Good morning or good afternoon, whatever time you're listening to this. This is a recorded class for Calculus Honours on April the 2nd, day 2. What we're going to do here, we're going to continue on from what we did on Wednesday, April the 1st, where we were talking about concavity and points of inflection. This video, this page that I'm looking at on OneNote is in your content library. I think I've also sent it around to your own individual notebooks. It's under the e-learning tab, and because it was from April the 1st, the title on the page is Day 1, April 1, Concavity and Points of Inflection. So hopefully you're able to find it. Yesterday, the last time we met together as a class, we looked at the introduction to this page where we talked about concavity, graphs that are concave up, graphs that are concave down. We talked a little bit about the behavior of secants and tangents in relation to graphs that are concave up and down. And we said that in reality, most graphs, or many graphs, change concavity at some point. So this is, I guess, around the point where we're looking at. The graph here begins concave down. At the red dot, it switches to concave up, and at the second red dot, it switches to concave down again. Those red dots are approximate locations, and the points where a graph changes concavity, so the points where a graph changes concavity, are called points of inflection. Okay, so the focus of yesterday's class was the idea of concavity, and then this concept of points of inflection. Points of inflection, points where the concavity changes. Right at the end of that class, we talked about why points of inflection are important. We talked about it in the context of the coronavirus. And we said points of inflection in reality and real life situations, whether you're talking from a business perspective, a scientific perspective, points of inflection are important because they're the point at which a function is increasing or decreasing most quickly. And once you're past the point of inflection, the quantity will continue to increase or decrease whatever it was doing originally, but it will now do so at a slower rate. So in terms, again, relating this to the COVID-19 virus, when the COVID-19 virus, when it spread or when the incidence passes its inflection point, you'll hear that in the media. It will mean that the virus is still spreading, but it won't be spreading as quickly as it has done up to that point. We still won't be over the worst. The number of cases will continue to grow, but they won't grow as quickly as they did before. So we'll have begun to flatten the curve. And like I said here, it's important to point out we won't recognize the point of inflection until well after we've actually passed it. You can't see it in the present, you only see it in the rear view mirror, if you like. So what is this class going to do the next 10 or 11 minutes? We're going to look at how we would accurately locate inflection points. Okay, we said, going back to this graph, that it's very hard to specify where exactly the points of inflection are. The red dots give you sort of a ballpark estimate of where they are. The points of inflection are close to those locations, but I can't say exactly where. So here's the start of today's class. How do we accurately locate inflection points? And the answer is with calculus. Okay, so what we're going to do, I've said before that it's impossible looking at the graph of a function to say exactly where the point of inflection is. However, if you use both first and second derivatives, actually you can use either of them, one or the other, you can readily identify the point of inflection. So just the way we did previously with relative maxima and relative minima, I'm going to give you all the information in a table. Okay? So remember, the questions we are going to be asked are about... Oh, sorry, that's definitely not what I wanted to do. The questions we're going to be asked are about the original function. So this is what we're going to be asked about. But what we're actually going to see is either the graph of the first derivative, okay, we're going to see either the graph of the first derivative or the graph of the second derivative. Okay, so we're going to see the graph of the first derivative or the second derivative, but we're going to be asked to answer questions about the original function, which we will never see. Okay, we're not going to see the original function, but we'll be asked about it. So it may be easier now to get rid of all of this stuff again. Get rid of all this. But the thing you have to remember here is that you're going to be shown either the first derivative or the second derivative, but asked about the invisible function. Same as we did with relative maximum, relative minimum. So when the original function is concave up, the first derivative would be increasing, the second derivative would be positive. Don't worry about why this is. I'm not going to go into that. If we had time in class, we would probably spend the time doing it. But these are just relationships that I want you to try and learn. When the original function is concave down, so if you have a function that's concave down, its derivative will be decreasing and its second derivative will be negative. Okay? Remember, positive, when we talk about second derivative here, positive means above the x-axis, negative means below the x-axis. When the original function has a point of inflection, then the first derivative would either be changing from increasing to decreasing, or possibly from decreasing to increasing. Again, when the original function has a point of inflection, the second derivative will either be equal to 0 or undefined, and it will change sign. That and changes sign is important. So there's two examples here, and your homework is going to be based on these examples. And you're going to have to initially pay very close attention as to whether the graph you're shown is a first derivative graph or a second derivative graph, because that will influence how you use the table. So let's do example 1. So in example 1, it tells us to study the graph of f prime. The derivative of a function f is shown below, and answer the questions that follow. So it's f prime, right? So f prime means we're looking here. Okay, we're looking here. We want to answer questions about f, but we're going to look here. So the questions are here at the bottom. Write down the intervals on which the function f, which is not shown here, is, and I've made a mistake. Oh my goodness gracious me. That should be concave up. I apologize. And this one should be concave down. I've probably made the same mistake below because I copied and pasted. Concave up. I beg your pardon for this. Concave down. Okay, so you may need to change that in your own individual notebooks as well, unfortunately. I'm very sorry about that. Okay, so let's go back up here. So you want to know where f is concave up. Okay, now I did leave room down here for writing the answers, but I'm actually going to put the answers here because it's makes more sense. Okay, so A. So you want to know when f is concave up. So f is concave up. That's what we're looking for. Well, go back up to your table. Now you're showing the graph of f prime. So we're looking at f prime for f prime. So f is concave up. F is the original function. F is concave up when f prime is increasing. So what you want to do is you want to look at f prime and see where is this graph here increasing. Where is it going up? And it starts going up here when x is 2. So it starts going up there at 2, and it continues going up until it gets across to 5. When f prime is increasing. So that means, beg your pardon, sorry about that interruption. That means from I need to check that actually. Okay, from 2 to 5. Okay, so f is concave up and f prime is increasing. That means from 2 to 5. The second question, if we look down below, write down the intervals in which the function f, which is not shown here, is concave down. So now you want f to be concave down. Okay, so f is concave down. Look it up in your chart. Where is f concave down? F is concave down when f prime is decreasing. So where is f prime decreasing? Well, it starts decreasing at -3. It's flat up until -3. So we're not going to include this part of it. We're not going to include this part of it. It's flat to -3. And then it starts coming down, and it comes down all the way until you get to 2. So from -3 to 2. F is concave down when f prime is decreasing. Okay. And then C. Write the x-coordinates at which f, not shown here, has a point of inflection, and in each case justify your answer. Okay, so we want f to have a point of inflection. So f has a point of inflection when f prime changes from increasing to decreasing, or from decreasing to increasing. So if we look at this, try and write this down. We're flat here. We're decreasing here. We're still decreasing here. And then at that point, we start increasing. Okay? So where does that change take place? And it takes place when x is 2. Okay, so f is a point of inflection. So it's justify your answer, so we have to say why. So f has a point of inflection when x equals 2, because f prime changes from, so it was decreasing first of all, decreasing to increasing. Okay, and that's almost bringing us up to 13 minutes, so we're not going to have time to do the next one. Okay, go through this video as often as you need and watch especially the example, and then for homework I want you to go down here to where it says homework given on April 2nd. It originally said April 1st, but we didn't get to it yesterday. And what I want you to do on this question are A, C, and D. Okay, those are all first derivatives. The other three are second derivatives, so we can't do them yet. So A, C, and D, that'll be your homework. That will be due on Friday morning, before 8 o'clock on Friday morning. Okay, thanks for watching. I know it's a longer video than I intended. I would thank you and apologies for the mistake that crept in there. Take care.